So, is Wireguard overhyped? That's the question I'm trying to answer today, specifically for client VPNs. This is where you have a bunch of users, such as employees, friends, and family, and you want them to connect back to your network to access resources on your network securely. I'm not talking about site-to-site VPNs or those sort of remote access geolocation VPNs. I'm specifically talking about client access today. So, is Wireguard overhyped for that use case? So anyway, if Wireguard versus OpenVPN sounds good to you, then come along on this adventure. Now, Wireguard is known for being a fast and efficient protocol, but they've made some choices that won't make it scale super well, especially if you have hardware that supports hardware-accelerated AES. So Wireguard is based on the Noise Protocol Framework. That's a method of establishing secure connections cryptographically. They've chosen as their cipher to use SHA-20 Poly 1305. That's an AEAD or authenticated encryption cipher. It's a very good cipher, but it doesn't hardware accelerate as well as AES. And since AES and SHA-20 crypto benchmarks show AES is about 10 times as performant as SHA-20 on modern Intel CPUs, I thought maybe OpenVPN might give Wireguard a run for its money with the relatively new kernel-based data channel offload. Another advantage that OpenVPN has is that it actually has features that can authenticate users. So Wireguard purely uses the peer's public key as the only method of authentication. There is no way to do two-factor authentication. There's no way to ask for a username and password. There's no way to set an IP address. If you want to do anything, the Wireguard developer says you should implement it yourself outside of Wireguard, and he's not going to help you. And that's certainly an approach to take. But for client access VPNs, it's certainly nice to be able to push configs to the client and have a respectable client-server-based approach. We can ask the client for credentials. We can use a variety of different authentication methods, such as certificates, or usernames and passwords, or usernames and passwords plus two-factor, things like that. So today, my hardware test setup is going to be this box right here. This is an older Protectly FW4C. This was one of their first units to include 2.5 gig Ethernet, so it's got 4 2.5 gig ports. But by 2025 standards, it's quite a poor choice. It's a 7th gen Intel processor, so that's, I don't know, like 8 years old at this point. And I chose it specifically because of its age and its 2.5 gig NIC. So I have a bit of a choice to make here on how I benchmark these. In my lab here, I have a lot of 10 gig equipment. So I could set up fast machines at 10 gig and try to measure the CPU usage at 10 gig. So that system, for example, could probably handle both Wireguard and OpenVPN at 10 gig. I don't doubt it. But it would probably use most of its CPU doing that. So I would need to have 3 nodes set up: my target, my router, and my client. And the client and the router would both need to be able to support 10 gig throughput with both of these algorithms for me to measure the CPU usage on the router. So I would need a pretty beefy client, and I could use my desktop for that, that's fine. But my other approach I could take is to use a really low-end processor, peg the processor at 100% and measure what bandwidth I get. So this thing supports 2.5 gig. I would be very surprised if it can do either Wireguard or OpenVPN at 2.5 gig. So given that limitation, I can run this thing at 2.5 gig and measure what bandwidth I actually get, and use that to extrapolate performance across Intel x86 based CPUs, and probably AMD as well. Of course, none of this applies to ARM. ARM crypto is a bit different, and that's one of the reasons why Wireguard chose SHA-20, because on systems which don't have hardware accelerated AES, AES is very slow. But in this case, I'm talking about an application like a VPN concentrator. You have all your employees VPNing in. How much load it adds to each of their computers is probably not a concern for you, especially because they're probably not pegging 2.5 gigs like you are on the router end. So the efficiency on the router end is very important for this particular use case. So anyway, it's my test setup. I'm going to be running plain vanilla Debian today. I am going to run the latest testing kernel. So I'll be running Debian 13 Trixie, which is currently in testing, not released yet. And that should give me a fairly recent Linux kernel to test with. I'm going to be testing Wireguard, which is obviously in kernel. And I'm going to be testing OpenVPN using their kernel-based data channel offload. Now DCO is also available for FreeBSD if you're a user of OpenSense. If you're a user of pfSense, they don't compile it for pfSense CE intentionally, because they want you to buy pfSense Plus. So I got 3 nodes in my test setup. So I got the firewall itself, which I named WG Metal. I'm running Debian Trixie and Linux 6.12. That sits here off of my regular home lab LAN, and it gets a regular home lab LAN IP address. Then I have a client, which is going to represent my client. It again has a regular IP address, and it's going to make VPN connections across the home lab LAN to the firewall. On the bottom side, I've got this whole network that's simulating like your enterprise dial-in network. I've got a server, my test destination, that's at 2001 DB873, so we'll have to type that in later. And this node up here, the test source client, it can't route to the server unless it goes through the firewall. So this firewall is our firewall router. I'm not running a firewall in this test, but it's my routing appliance. So when I bring the tunnels up, they'll end up being here, so they'll be between my client here and my firewall here. And then the client can route via the tunnel to the firewall to get access to this internal network down here. So this is the part that's encrypted. We're doing decryption here at this firewall box, and then routing from there to my test server. Now in reality, this is a physical box, bare metal. It's got two 2.5 gig Ethernet links, which are physical links, they're not VLANs, and that goes up to my sort of private cloud, where these guys run in a virtual environment, and I have enough bandwidth through the cloud to run it out to these two physical lines here that run to the firewall. So these are not real clients, they're just virtual machines, and I'm just monitoring the VMs and making sure they're not hitting any CPU limits here. Before I get too far along, I want to make sure all of these routing links are working properly, all of my traffic's flowing the right direction, etc. So a quick IPerf test from the router to the destination. I'm getting about 2.32 gigabits per second. It's exactly what I'd expect over 2.5 gig Ethernet. Of course, this is 2.32 gigabits per second after TCP and IP and MAC overhead. 2.5 gigabits is the frequency on the wire. And similarly from the source to the router. Oh, that's not right. That's not right. Fuck. That's why we do these tests. I have one of these that's connected to PoE and one that's connected to 10 gig, and I just kind of used them both on my bench, and I had the wrong ones connected. So I was getting 10 gig to the Jet KVM that doesn't really need 10 gig, and that should have fixed this problem. There we go. Now we're getting 2.32 gigabits per second like we expect. Perfect. So now that I know that my links are running at 2.5 gig, I'm going to set up the most basic of tunnels. That is an IPIP tunnel. That will force my client to encapsulate its traffic, send it to the router to be decapsulated and routed. Now this isn't going to do any sort of encryption. There's no sort of framing. There's just the IP packets inside of IP packets, the most basic of tunneling. So I set up an IPIP tunnel. I've got an address on the tunnel and then over on the server. So on the server I have an address on the tunnel, but then I also have an address on the local subnet. So I go over here and I'm going to the remote server with IPerf. Looks like we're getting not quite the same bandwidth we had before, so there's a little bit of overhead. And that's expected because we added a bit of header space with IPIP. And the system is using a heck of a lot of time doing IRQs for the network interface, which makes sense. So technically, this IPIP tunnel would be single-threaded. And let me explain why. So here I got this example. We have a network card. It's connected to the Ethernet, and it has 4 queues, and each of these queues is tagged to one specific CPU core. So when this queue fills up, that CPU core will process this queue. And this is a really common and really efficient way of processing a lot of packets, so we don't bog down just one CPU core with processing all the frames coming in from a network card. So a frame comes in from the network card has to decide which queue to send it to. And it does that by looking at the layer 2 and the layer 3 source and destination MAC address and IP address. So based on layer 2 and layer 3 addresses, it takes a hash and decides which of these 4 queues to send it to. So we'll say it's sent it to this one. So now we get another packet coming in on the wire. It takes its hash again. Let's say it's from a different MAC address this time. So this time it goes over into this queue. And so these 2 different flows here with these IP and MAC address pairs would end up on these 2 CPU cores. But for IPIP, our source and destination IP address outside of the tunnel will always be the same. And actually this applies to pretty much any VPN tunnel. So when we take the hash, we're going to get the same result. Our MAC addresses should be the same. They're going to be destined for this node from the router. Our IP addresses should be the same. So all of our IPIP packets are going to end up going into the same queue. We'll end up with one queue filled with all of our IPIP packets being handled by one CPU core. And actually this is also normal. So in this case, that interrupt request, k-softirqd, is only going to be used for handling the net filter part. So it's going to do the firewall, it's going to do the route, and in this case, it's going to decapsulate the IPIP packet because that's done in kernel. But for Wireguard and OpenVPN, it would not be handled by this core. This would just do the initial packet processing. Then it gives it off to somewhere else in the kernel. But since IPIP is done in kernel in NetFilter, this one core will end up doing all of our IPIP. But since IPIP is so easy, it's not a problem. We're not using that much CPU load to do 2.5 gig IPIP. Oh no. Oh no. What are you mad about now? NetDev Watchdog, CPU transmit queue time down. Oh, shit. You guys are Rev 03. You're not supposed to be doing this to me. So it seems like I'm being bitten by the fact that Intel completely dropped the ball on their 2.5 gig NICs. For a long time, if you wanted a very reliable network card for like a FreeBSD-based router, for example, the recommendation was certainly to buy Intel. Their driver support is great. And then the Intel i225 came out, and it was so bad they had to do 4 hardware revisions to fix all the bugs. That's why they call it the i226 now, so people don't get confused with the first one that was buggy, one of these.
A few moments later.
Okay, so I got Wireguard up, I got the config in the blog if you want to see it. And now we can run iPerf. Let's go find iPerf in my command history. Okay, 2001 DB873. Let's see what we got here. So we are maxing out at 1.8 gigabits per second. That is less than 2.5. So SoftIRQD is the network card driver, and WireGuard Crypto is using an outrageous amount of CPU here to do crypto work. So how does WireGuard end up dealing with this queuing situation? So just like in IPIP, all of our WireGuard packets outside of the tunnel will have the same source and destination IP address. So they should be hashed the same. That means they'll all end up in the same queue handled by the same core in NetFilter. But WireGuard doesn't do crypto in that core. It hands it off to another work queue. So WireGuard has its own work queues which handle the packet once it's been passed into WireGuard. So when WireGuard processes the packet in NetFilter, NetFilter hands the packet to WireGuard in the interrupt, and WireGuard will enqueue it in one of its own queues to do crypto work. And so each of these guys here will end up going into a different WireGuard queue, just like that. And so now WireGuard can distribute the crypto work across multiple cores very efficiently. So I'm happy to say we have successfully pegged this hardware at 100% utilization. And to peg all those 4 cores, we got 1.79 gigabits per second, which is really not bad. Even this appliance, which at this point is almost 5 years old, would be perfectly fine for this kind of work still today. But we're trying to compare this to OpenVPN. So if OpenVPN is faster than 1.79 gigabits per second, using kernel data channel offload and AES, then we'll have a winner.
6.5 hours later.
It is now a few hours later. I have been fighting with OpenVPN this whole time over the very stupidest things, such as the key usage attributes in my X509 certificates. But I figured that all out now, and the blog post will have instructions on how to replicate this. And I am getting a whopping 150 megabits per second. That's pretty shit. Now I'm not using data channel offload yet, so this is just running on the poor CPU here. So if I hit top here, it looks like we are completely pegging OpenVPN. Ooh, and OpenVPN is single-threaded. That's rough. So being single-threaded, at least per connection, we're spending basically all of our time in the OpenVPN thread, but we're only using 1 core. So we're not using all 4 cores the system has. Now I'm not sure if OpenVPN is just single-threaded, period, or if it's threaded per client. I only have 1 client running now. But in either case, that's a pretty awful performance metric. So let's see if data channel offload can fix that. So let's install headers. So we needed headers because OpenVPN DCO is a DKMS module and it needs headers. What the? Okay, that was my bad. It's actually OpenVPN DCO DKMS. So now that will install and then it will compile itself and we can load it into the kernel. DKMS is a cool tool that will dynamically recompile kernel modules every time you update your Linux kernel. Okay, so we got a new kernel module. I'm going to mod probe it. Mod probe OVPN DCO v2. Hello. And just to be clear, it says it has a DCO device, ton 0. So what do we get this time? What's better? It's definitely better. We've roughly doubled our bandwidth now. So here we are stuck in what appears to be a, maybe not quite single-threaded. We seem to be relatively thread-bound here as well, from a single thread and a single client. But we're doing better. So by using the data channel offload kernel module, we were able to push OpenVPN from 1/10 the performance of Wireguard to 1/5.
One eternity later.
So after staying up till 2 in the morning fighting with OpenVPN, I concluded that the problem with OpenVPN is code quality. Wireguard just has much better code than OpenVPN, and the fact that they're running in kernel gives them a performance boost for sure, but OpenVPN's code even in kernel is still really bad. So a bit of visual representation of what's going on here. We again have our multi-queue NIC here. These interrupts are processing packets that go to OpenVPN. OpenVPN now is running in user space, so it has a ton tap adapter here. And so we need a queue for OpenVPN. So now OpenVPN is only implementing one queue. So all of these packets here have to queue up in this single queue on their way to user space. And then they have to get processed by OpenVPN and sent back. And this is only single-threaded, so even though there's only one queue here, we could have multiple queue workers in user space pulling out of the same queue, but we don't because OpenVPN is single-threaded. So you'd think, now that OpenVPN is in the kernel, it could run multiple workers to process these multi-queue NICs, right? So maybe like WireGuard, we could have a couple different queues here, and we could deal with the packets on multiple cores. But that doesn't work either, because OpenVPN in the kernel also is limited to just one single queue and one single kernel worker. But it gets even worse. The OpenVPN kernel module has one singular queue to be processed on one singular core for the entire kernel module. So if we make more than one OpenVPN server, which normally would be multi-threaded because each server is its own independent process, all of those are sharing the same work queue in the kernel, the same one work queue. So even if I create 4 different OpenVPN servers with different configurations, they're still all single-threaded in the kernel in DCO. Now if I ran them in user space and did this toss through the ton adapter up to user space, then I would have 3 separate threads for my 3 separate processes. But then I don't get the advantage of speed of processing in the kernel. So really, OpenVPN just all around has design constraints that fundamentally limit its multi-core ability, and that just doesn't scale well in the modern era. So OpenVPN Access Server, the commercial product, will run multiple copies of the single-threaded daemon for each core. So if you have a 4-core CPU, you'll get 4 daemons, probably 4 daemons, and they'll use IP tables, essentially round robin, to assign connections to be port forwarded to a higher number internal port, which then gets handled by the OpenVPN thing in user space. So that would mean my 150 megabit single core were turned into 600 megabits quad core for 4 clients, assuming they get round robin correctly. So in aggregate, that does work. You get averages, but still 600 megabits is a lot less than 1800. But anyway, there is another VPN solution that is even easier to set up for clients than WireGuard because it's built into every modern operating system. It's a lot more work to set up for admins because it's a huge pain to set up, but that's IPSec. Just to prove how easy it is, I'm going to go ahead and set up the client here right now live, no cuts. So I need my server address, which is also going to be the ID of its name. I'm going to authenticate with a username and password. I guess we'll be admin5 today. And we'll go ahead and create that, and boom, our tunnel is up and ready. So since all the settings came from the server, all we needed was the server's address and our username and password. That's it. So anyway, IPSec has some of the advantages of WireGuard. It runs in kernel, so we shouldn't have to do user space transitions. It should be fast. It can use AES. It can use AES with AED ciphers, authenticated encryption ciphers. So we should be able to use like AES 128 GCM or AES 256 GCM and get blazing fast performance. So I tried that, and I again encountered some issues. Aside from the issues of setting up Strong Swan and Sharon and those daemons. So coming back to my queuing analogy for IPSec again, IPSec done in kernel is done directly in the netfilter network card interrupt. So even though IPSec could be handled by multiple cores, it might not be. So if you have a tunnel that has the same source and destination IP address, they all end up on the same core, those packets are all going to be processed by the same core for IPSec. But if you have traffic flowing in both directions are handled by whichever network card receives the traffic. So those can be bound to different cores. And also, if you have more than one tunnel going, those could end up on different cores. And in my setup, I had multiple clients with multiple IP addresses. And since their IP addresses were different, they ended up getting hashed into different queues, and I could spread them across the cores pretty evenly. So that means that with one client, I was limited to 700 megabits per second, which is not that bad for a single core. And if you follow that logic along, 700 times 4, you get 14, 21, 2800 megabits per second, which is a lot faster than WireGuard, isn't it? So in the end, my scaling didn't work out that well. I ended up at 2200 megabits per second. Remember, I'm limited by about 22 to 2300 just based on packet overheads, 2.5 gig NIC. But my setup wasn't stable. I kept crashing the network card driver. Remember back with IPIP, the network card driver kept resetting? That was happening again to me in IPSec. So I'm pushing the limit of what this network card can handle. But that's better than WireGuard. But again, that is with 4 separate cores running 4 separate SAs to 4 clients, because one single client ends up getting binned to the same core by consistent hashing. But thankfully, all my infrastructure for this test is virtual, so I can just copy and paste my sources and copy and paste my destinations, have a whole cloud full of them, and then I can run 4 clients worth of throughput through this guy and get them on multiple cores to do a full multi-core test. So maybe at this point I'll make a graph or something of the performance and how bad OpenVPN was, even with data channel offloading kernel, and even with multiple clients, because I did copy and paste my clients and copy and paste my servers, and OpenVPN was still pretty bad. So before you head down into the comments to argue, I would like to ground this discussion saying that I intended to focus entirely on traditional client access VPNs for this video. So this is where you have a bunch of users, probably employees, they're mobile, on the road, working from home, etc. They're all dialing into your corporate network. This is a very traditional way of using VPNs. I'm aware there are a lot of new topologies out there, like zero trust mesh networks, things like that. I'm not talking about those today. So in that specific use case, there's not a huge uptake of use of WireGuard. A lot of legacy companies are still using IPSec. A lot of people are still thinking about OpenVPN, mostly because of the advantages it has in terms of managing clients. So with WireGuard, there is no managing of clients. They use bare public key authentication, which is secure, but it doesn't identify the client by anything more than their public key. So we don't have any sort of user credentials that we can cast along. We can't add two-factor on top of that. We don't have expirations of certificates. None of that happens with WireGuard. We also can't push configs to the clients from the server, so we have to send out new config files to our clients every time anything changes. The advantage of WireGuard, the stated advantage, is that it's very fast. So I wanted to see how that stacks up to the feature set of OpenVPN and later IPSec. So coming into this video, I had the assumption that WireGuard would be fast, but OpenVPN might be able to catch up with hardware acceleration and data channel offload and kernel and things like that. And I was surprised to find that it's just not the case at all. What did surprise me, though, was just how performant IPSec is. So IPSec is a rather old protocol. People tend to hate on it, but it seems like some of that hate is kind of undeserved. Recently had a discussion in my Discord server about why companies aren't switching from IPSec to WireGuard or a WireGuard-based solution. And one of the people said basically, we don't care how much faster it is. If it's not saving us at least 40% of our budget for VPN solutions, it's not worth implementing. And WireGuard is clearly not faster than IPSec, and IPSec provides a bunch of advantages like pushing routes and pushing IP addresses to clients. So why would you switch? If you have already invested in setting up IPSec infrastructure, it's better than WireGuard. I mean, the setup process is very painful, sure, but you've already gone through the setup process. Why would you switch to WireGuard now? Now, the other assumption I had in my mind was that some companies are restricted by FIPS compliance. Well, I don't work with any companies that have strict crypto compliance requirements, but my understanding is the federal government's FIPS, the US federal government's Federal Information Processing Standard, does not allow the use of ChaCha20, just period. The only cipher approved is AES. That would naturally mean WireGuard also can't be used. NIST has standards on how to implement VPNs. They have standards for IPSec and SSL VPNs, which are based on the TLS protocol, such as OpenVPN, but also others. And they don't have one for WireGuard, and they can't have one for WireGuard, essentially until ChaCha20 is an approved cipher. And we're getting there, but we're not there yet. But in reality, most industries are not directly tied to FIPS. If you're doing like PCI credit card compliance, I believe they allow WireGuard. They're just looking for a certain security level, not necessarily government-approved encryption. And some of the reasons ChaCha20 might not be approved could be sort of tinfoil hat NSA stuff as well. Also, for the purpose of this test, I was trying to give OpenVPN and IPSec their best chance. I ran them with AES 128 GCM. That is GCM is a very modern cipher. It's authenticated encryption. 128 is the lowest security level allowed by AES. It's still believed to be fully secure. However, some standards bodies are starting to recommend moving to 192 or even 256-bit AES over the next couple of years. So the data I've heard is that by 2030, they want to be moved off of AES 128. I did test IPSec with AES 256 GCM. Now AES 256 uses 14 rounds instead of 10, so I should expect to see about a 30% drop in performance, and that's pretty much exactly what I saw. Went from 700 to 500 megabits per second. So the math works. I'm sure I'm going to have a bunch of you guys arguing in the comments about Tailscale. Tailscale is a mesh VPN. It's not a sort of access VPN like this. I'm aware it exists. I don't use it because I use a better solution called Nebula, which is also a mesh VPN, which is also why I didn't cover it in this video, etc. As for site-to-site VPNs, I'm sure there are probably good reasons to use IPSec, especially if you have IPSec hardware offloading in hardware. Then it would be crazy to use WireGuard and software over IPSec. But IPSec still seems to be holding a slight performance advantage there. WireGuard has the advantage of being very, very easy to set up. So in this video, it took me like less than 15 minutes to handwrite my WireGuard config and also write the blog post for my WireGuard config and test it. It took me a couple hours to do that in IPSec. It took me even more hours to do that in OpenVPN. So I, of course, welcome all of your comments and arguments. I do love when you guys boost my engagement in the comments by arguing. So anyway, head down to the comments section. If you want to try any of these things yourself, I have a link in the blog post below that shows the commands I use to set these up. I was not trying to run a long-term test. Many of the commands I'm running will not survive a reboot. If you reboot the system, they're not going to come back up correctly. I know that. I'm just trying to test things here, so I'm not automating any of it. But yeah, if you want to chat with me, I have a Discord server link down below for that. It's always fun talking to you guys there. If you want to give me a tip, I have a Ko-fi link down below for that as well. It's kind of like a Patreon, but it's only a one-time thing, not recurring. And as always, I'll see you guys on the next adventure.